The middle of the 20th century. The aviation industry of the United States is gripped by a real speed fever. Every new fighter must fly faster than the previous one. Every new project is obliged to break the sound barrier, and engineers compete with each other in who will be the first to squeeze another 100 kilometers per hour out of a jet engine. And right in the middle of this race, the United States Navy Command does something completely inexplicable. They order a subsonic attack aircraft, neither supersonic nor experimental nor breakthrough, but deliberately slow, cheap, and deprived of everything that the newest machines of that time were proud of. The aviation world perceived this decision as a step back, as an outright surrender to progress. But it was this strange choice that led to the appearance of one of the most effective combat aircraft in the history of the American fleet. To understand why this happened, one must return to the late 40s and early 50s, when American combat aviation was going through a period of turbulent and chaotic changes. Jet engines had only just become the basis of military aviation. The very concept of avionics was only forming, and design bureaus across the country were producing one ambitious project after another. Each new aircraft was bolder and more expensive than the previous one, and each of them carried some revolutionary idea, whether it was a new wing scheme, an experimental fire control system, or a previously unseen fuselage layout. The problem was that most of these machines became obsolete faster than they could enter service. While one aircraft was undergoing testing and refinement, the next, even more perfect and even more expensive, was already appearing on the drawing boards. The military budget was bursting at the seams because each such project required colossal costs for research, development, and production, and the service life of the finished machine turned out to be annoyingly short. Aircraft manufacturing companies chased records and contracts, and the fleet received magnificent but impractical machines that were difficult to maintain and expensive to keep. A bright example of this era was the Vought Corporation, one of the oldest American manufacturers of carrier-based aviation. In the 50s, the company released the tailless fighter F-7U Cutlass, a machine so advanced in design that pilots nicknamed it the Ensign Killer. The Cutlass looked futuristic, but flew terribly. It suffered from constant engine and hydraulic failures, and its landing on an aircraft carrier deck turned into a game of roulette with death. The aircraft was decommissioned ahead of schedule, and it remained in history as one of the most dangerous machines ever accepted into service by the American fleet. However, the next Vought project proved to be much more successful. The supersonic fighter F-8U Crusader became a truly outstanding combat machine, fast, maneuverable, and reliable. The Crusader earned a reputation as a magnificent platform for aerial combat and served in the fleet for many years. But it had a serious drawback that became critical with the start of the Vietnam War. The Crusader remained primarily a fighter. Its main weapons were cannons and missiles for aerial combat. And as an attack aircraft for working on ground targets, it was poorly suited. In addition, it was expensive, and its maintenance on aircraft carriers required significant resources. Meanwhile, the Vietnam War was gaining momentum, and the American fleet faced an urgent need for a completely different type of aircraft. The main carrier-based attack aircraft at that time remained the A-4 Skyhawk, a compact and reliable aircraft that had performed excellently in previous years. But the Skyhawk had a limited flight range and could carry only a relatively small combat load, which made it increasingly unsuitable for the tasks set by the new war. The fleet needed an attack aircraft capable of operating at a significantly greater radius, delivering many more bombs to the target, and at the same time not ruining the treasury either in production or in operation. And then the Navy analysts did what the military rarely do. They conducted a large-scale and impartial study. A special group for the study of fleet airstrike forces analyzed 144 hypothetical aircraft variants, differing in speed, size, engine type, and combat capabilities. The result of this study turned out to be so unexpected that even the authors themselves found it hard to believe. It turned out that a subsonic light attack aircraft is capable of performing strike tasks at low altitudes more effectively than any supersonic competitor. Supersonic speed, which everyone was chasing, turned out to be practically useless when attacking ground targets from low altitudes, but it monstrously increased the cost of developing and maintaining the aircraft. This was a turning point. The Fleet Command made a decision that seemed absurd against the backdrop of the general obsession with speed, but was backed by cold calculation and figures. The fleet put forward tough requirements for the new aircraft. The attack aircraft had to have at least twice the flight range of the Skyhawk and carry twice the combat load. At the same time, the machine was obliged to remain compact to fit on the deck and in the hangars of aircraft carriers, withstand the harsh conditions of maritime operation, and, what is especially important, be cheap, both in production and in maintenance. To shorten development times and reduce risks, the command demanded the use of the airframe of an already existing and proven aircraft as a basis. No one intended to start from a clean slate. Time was pressing, and the war did not wait. The Vought Corporation accepted the challenge. Engineer Russell Clark, an experienced designer who perfectly knew the capabilities and limitations of carrier-based aviation, was appointed to lead the project. Clark immediately gathered a team and determined the starting point for the new attack aircraft. The base was to be that same Crusader, a supersonic fighter that had already proven its reliability and strength in real combat conditions. But the task was not just to modernize an existing machine, but actually to create a completely new aircraft based on it with a fundamentally different purpose. The first thing Clark's team did was get rid of everything related to supersonic flight. The Crusader was born for speed and aerial combat, but the new attack aircraft was to hang over the battlefield for hours at low altitudes, accurately hitting ground targets. The afterburner, which devoured fuel and was completely unnecessary for an aircraft not claiming supersonic speed, was removed from the design. Instead of the powerful turbojet engine J57P28 that was on the Crusader, they installed the turbofan Pratt and Whitney TF30P6. This engine was more economical, quieter, and significantly better suited for long flights at medium and low altitudes. However, the new engine required a huge amount of air, and this is where the most interesting part began. The engineers placed a massive air intake in the nose of the aircraft, which literally defined the entire appearance of the machine. This giant funnel in the front part of the fuselage made the aircraft look like anything but a sleek fighter. Pilots, seeing the new machine for the first time, immediately dubbed it SLUF, which stood for Short Little Ugly Fellow. The nickname stuck for good, but those who designed this air intake cared least about the appearance. The simple design of the inlet channel ensured a reliable air supply to the engine in all flight modes and during all maneuvers, and the absence of complex adjustable flaps required for supersonic aircraft simplified maintenance and reduced the probability of failures. True, this same air intake created an unexpected problem on the deck. The huge funnel in the nose of the aircraft sucked in air with such force that it presented a real threat to the aircraft carrier deck crew. Technicians and sailors working near the aircraft with the engine running risked being pulled into the air intake. They had to develop special safety protocols and establish strict restricted access zones around the nose of the machine when the power plant was working. The wing of the new attack aircraft also underwent serious changes. The Crusader had a unique variable incidence wing, which allowed for an increased angle of attack when landing on an aircraft carrier. For the attack aircraft, this complex and temperamental system was removed, replacing it with a simpler and stronger wing with a large number of hardpoints for weaponry. Numerous pylons were placed under the wings and on the fuselage, on which bombs, missiles, and external fuel tanks could be hung in a wide variety of combinations. It was this flexibility in armament options that later became one of the main trumps of the machine. The fuel system was completely redesigned. Internal tanks were significantly increased in volume, squeezing the maximum space for kerosene out of every free space inside the fuselage. In addition, an aerial refueling system was installed on the right side of the nose, which allowed the attack aircraft to take fuel from aerial tankers right in flight. This decision further expanded the already impressive combat radius of the machine, giving it the opportunity to strike targets that no carrier-based attack aircraft of the previous generation could reach. When the prototype finally took to the air, the test results amazed even the designers themselves. The flight range was about 8,800 miles, which was 4 times higher than the capabilities of the Skyhawk. The maximum combat load exceeded 20,000 pounds, which was a simply fantastic figure for an aircraft of this class. And with all this, the new attack aircraft turned out to be even slightly faster than its predecessor, although speed was never its priority. The machine turned out to be exactly as the fleet wanted to see it. A workhorse capable of carrying a huge load over a huge distance and doing it reliably, time after time, day after day. Production began to gain momentum, and then the only serious hitch arose. The Pratt & Whitney Company, which produced engines for the first series, could not cope with the simultaneous fulfillment of military and civilian orders for this motor model. The engine shortage threatened to slow down the entire program, and management had to urgently look for alternatives. A solution was found fairly quickly. Subsequent series of the attack aircraft began to be equipped with other power plants, including Pratt & Whitney TF-38 and Allison TF-41A2 engines. The latter was a licensed version of the British Rolls-Royce Spey engine, which was famous for its economy and reliability. This was a successful move because the Spey had already undergone testing on European aircraft and proved to be an exceptionally hardy motor, capable of working in the most difficult conditions. The transition to new engines not only solved the shortage problem, but also allowed for the improvement of the characteristics of individual modifications of the attack aircraft, making it even better adapted to long combat sorties. But what truly set this aircraft apart from its competitors was not so much the iron and engines as what was inside the cockpit and in the electronic blocks under the skin. The filling of the Corsair II was truly revolutionary for its time, and in many ways ahead of even much more expensive and prestigious machines. In the nose part, right behind the air intake, was the ANAPQ-116 radar, later replaced by the improved ANAPQ-126 model. The radar was integrated into a digital navigation system, which in itself was a huge step forward. In the 60s, digital systems in combat aviation remained a rarity. Most aircraft got by with analog instruments and manual calculation of attack parameters. The Corsair II was a machine from the future in this sense. The radar transmitted data to an onboard computer produced by IBM, specifically developed for navigation and weapon control. This computer continuously calculated bombing parameters, taking into account the aircraft's speed, altitude, dive angle, wind direction, and strength. The pilot no longer had to rely solely on his own experience and eye estimation when dropping bombs. The machine itself suggested the optimal moment for attack, and the accuracy of hitting the target grew to indicators that the previous generation of pilots could only dream of. The computer also allowed for strikes from a greater distance, which reduced the risk of being hit by enemy anti-aircraft fire. But the main technological breakthrough was the head-up display. The Corsair II turned out to be the first combat aircraft of the United States to receive this system. Critically important information was projected onto a transparent screen in front of the pilot's eyes. Current speed, flight altitude, dive angle, lateral deviation, and the aiming mark for the attack. The pilot could conduct a battle without taking his eyes off the target and without lowering his eyes to the instrument panel. This seemed like a small thing, but in a real fight, when decisions are made in fractions of a second and the loss of visual contact with the ground at low altitude threatens a catastrophe, such a system literally saved lives. Very soon, The head-up display became a mandatory element of every American combat aircraft. But the Pioneer was precisely this unremarkable subsonic attack aircraft. The armament of the Corsair II reflected its multi-purpose nature. The first modifications carried 2 cannons installed under the nose part of the fuselage. Later, they were replaced by one 6-barrel rotating M61A1 Vulcan cannon, capable of firing thousands of shells per minute. Replacing 2 barrels with one multi-barrel block had practical sense. The Vulcan provided significantly denser fire when strafing ground targets, and its design turned out to be less vulnerable to return anti-aircraft fire from the ground. Pylons for air-to-air missiles, AIM-9. Sidewinder were located on the sides of the fuselage. This attack aircraft was not intended for aerial battles, but the command understood that over enemy territory, a pilot might encounter enemy interceptors, and a means of self-defense was necessary. Sidewinders gave the pilot a chance to fight off an enemy fighter and return to the aircraft carrier. However, the most impressive element of the arsenal became the guided bomb AGM-62 Walleye. This was a weapon ahead of its time by a decade. The Walleye was a gliding bomb with television guidance. The principle of operation was simultaneously simple and ingenious. On a screen in the cockpit, the pilot saw the image transmitted by a camera in the head part of the bomb. He aimed the crosshair at the target, locked the target, and pressed the launch button. After this, the bomb separated from the aircraft and independently glided to the selected object, and the pilot could immediately turn around and leave the kill zone of anti-aircraft means. Fire and forget. The accuracy of the hit at the same time remained exceptionally high because the bomb itself corrected its trajectory, holding the captured target in the center of the field of view of its camera. To protect the aircraft itself, engineers provided triple redundancy of the hydraulic flight control system. If 1 or even 2 hydraulic lines were damaged by anti-aircraft fire, the third continued to work, and the pilot maintained control over the machine. A significant part of the fuselage was covered with reinforced armor, protecting the most vulnerable units and the pilot himself from fragments and bullets of small-caliber anti-aircraft systems. In May 1970, the Corsair II went on its first combat mission over Vietnam. By this point, the war had already been going on for several years. The American fleet was suffering losses, and the carrier-based aviation pilots urgently needed a machine capable of delivering precise strikes on well-protected targets deep in enemy territory. The new attack aircraft had to prove its worth not on test ranges, but in conditions of real anti-aircraft fire, real jungle thickets, and real targets that shot back with everything they had. The first sorties showed that all calculations were correct. Pilots who switched to the Corsair II from other machines noted above all one quality that was impossible to overrate in combat conditions: predictability. The aircraft did exactly what the pilot expected of it. Without whims, without surprises, without sudden failures at the most inappropriate moment. The machine was responsive in control, stable on the combat course, and forgave mistakes, which was especially appreciated by young pilots who had not yet accumulated hundreds of flight hours. One of the most experienced Corsair pilots, David Olson, nicknamed Frosty, spent more than 3,500 flight hours in the cockpit of this attack aircraft and made 750 landings on aircraft carrier decks. He flew on practically all modifications from the early Series A to the late H, and knew the machine like no one else. Olson described the Corsair as a very stable platform with pleasant control, ideally suited for strike tasks, but he immediately honestly pointed out the main weakness. The aircraft quickly lost energy in a maneuverable fight. Without an afterburner, when attempting to pull turns with an enemy fighter, the Corsair rapidly lost speed. Olson described this feeling somewhat crudely but accurately, comparing the falling attack aircraft to something that falls from a great height according to the laws of gravity and without any elegance. Nevertheless, He emphasized that in skillful hands, even in aerial combat, the Corsair could stand up for itself. It was just not its element. Its element was attacking ground targets, and in this matter, there was no equal among carrier-based aircraft at that time. 1972 became the time of the most intensive combat operations for the Corsair. Within the framework of Operation Linebacker, American aviation unleashed massive strikes on North Vietnam, the goal of which was the destruction of transport infrastructure, bridges, supply warehouses, and weapons supply routes. Corsairs of the second series played a key role in these raids, rising from the decks of aircraft carriers in the Gulf of Tonkin and going deep into enemy territory to distances unreachable for attack aircraft of the previous generation. Simultaneously with strikes on ground targets, Corsairs participated in one of the boldest operations of that war, the aerial mining of North Vietnamese ports. The task was to block maritime supplies of military aid arriving in North Vietnam. Attack aircraft at low altitude entered the waters of the ports and dropped sea mines, effectively plugging the harbors for cargo ships. These were extremely risky sorties because the ports were covered by a dense ring of anti-aircraft artillery, and the low flight altitude left the pilot no room for maneuver in case of a hit. It was here that the survivability and reliability of the machine, triple hydraulics and armor, fully manifested themselves. Time after time, damaged aircraft returned to the aircraft carriers. The scale of Corsair's use in Vietnam was striking. In total, 854 attack aircraft of this type took part in combat operations, and together they performed more than 97,000 combat sorties. The overwhelming majority of these missions were strikes on ground targets from low altitudes, the very tasks for which the machine was created. Pilots time after time noted the outstanding bombing accuracy provided by the onboard computer and radar, which allowed for hitting point targets from the first pass without making repeated passes under anti-aircraft fire. The loss statistics for the entire Vietnam campaign turned out to be more eloquent than any words. Over the years of participation in the war, only 54 Corsairs were lost. For an aircraft that performed almost 100,000 combat sorties in the conditions of one of the most saturated air defense systems of that time, this indicator was exceptionally low. Critics who predicted that a slow, subsonic attack aircraft would become easy prey for enemy fighters and anti-aircraft missiles were put to shame. It turned out that for a strike aircraft working at low altitudes, speed was far from the main survival factor. Much more important were the strength of the construction, the survivability of systems, the ability to withstand combat damage and return to base, as well as the pilot's ability to precisely work on the target the first time and quickly leave without lingering in the shelling zone. A huge supply of fuel opened up another unexpected role for the Corsair. Thanks to the giant internal tanks, the attack aircraft could be used as an aerial tanker for other carrier-based aircraft. When escort fighters or scouts returned from a mission on the last drops of kerosene, it was the Corsair that could share fuel with them right in the air, saving both the machine and the pilot from a forced landing in the ocean. In total, about 1,500 Corsairs of the second series of various modifications were built during serial production. An aircraft conceived as a cheap and simple replacement for the outdated Skyhawk quietly turned into the backbone of the carrier-based strike aviation of the American fleet. Vietnam ended, but the career of the Corsair II was only gaining momentum. While dozens of other combat aircraft of the 60s and 70s were quietly retiring, being decommissioned and sent for storage in the desert, this ungainly attack aircraft continued to fly, fight, and prove its indispensability in every new conflict in which the United States engaged. In 1983, American armed forces conducted an operation on Grenada. A small Caribbean island was at the center of a geopolitical confrontation, and Washington decided on military intervention. Corsairs of the second series rose from aircraft carrier decks and struck enemy positions, providing support to Marine landing units. The operation was short-lived, but it once again demonstrated the key advantage of this attack aircraft over more modern machines. The Corsair could loiter for hours over the combat zone, waiting for a call from ground units, while faster and hungrier aircraft were forced to quickly return to the aircraft carrier for refueling. Time spent over the battlefield in such operations was valued more than any supersonic speed. 3 years later, the Corsair was back in action, this time over the Mediterranean Sea. In 1986, the conflict between the United States and Libya escalated. The American fleet conducted a series of operations off the Libyan coast, and carrier-based attack aircraft struck Libyan military facilities and air defense positions. Corsairs worked in conjunction with more modern aircraft, performing tasks of suppressing enemy air defenses and delivering precise strikes on radar stations and anti-aircraft batteries. The fact that an aircraft created in the 60s for the Vietnam War confidently acted against the air defense systems of the 80s spoke volumes. The Corsair's avionics, considered revolutionary at its creation, still remained at a level and allowed crews to effectively detect and hit targets. In December 1989, the United States began an operation in Panama, and here Corsairs of the second series again proved to be in demand, providing air support to land units. Attack aircraft worked over urban areas where surgical precision was required to hit military targets without touching civilian infrastructure. The Corsair's ability to deliver munitions precisely to the target laid into it during design turned out to be very useful here. But the truly final chord of the attack aircraft's combat career was Operation Desert Storm in 1991. When coalition forces began the air campaign against Iraqi armed forces, Corsairs of the second series were among those who delivered the first strikes. By this point, the aircraft was already more than 25 years old. An eternity by the standards of combat aviation, where equipment is updated every decade. Nevertheless, the veteran held its place in line on par with new generation machines. Attack aircraft attacked Iraqi fortified positions, armored vehicles, artillery batteries, and infrastructure objects, performing several combat sorties per day from aircraft carrier decks in the Persian Gulf. It was Desert Storm that became the last war for the Corsair of the second series. After the end of the conflict, the Fleet Command made the final decision to withdraw the attack aircraft from the combat composition. It was replaced by more modern machines, but none of them could boast such a long and rich combat biography. Throughout its entire career, the Corsair II performed more than 120,000 combat sorties in 5 different conflicts, from the jungles of Southeast Asia to the deserts of the Middle East. No other carrier-based attack aircraft of that generation could compare with it in terms of service duration and the number of real combat operations. The most striking thing in the history of this aircraft was not even how it fought, but why it appeared in the world at all. In an era when the entire aviation industry was obsessed with speed, complexity, and ambitious technologies, someone at the headquarters of the American fleet dared to go against the tide and bet on simplicity, reliability, and practicality. 144 hypothetical projects were analyzed before the military came to the conclusion that the best strike aircraft does not have to be the fastest or the most expensive. It should be the one that can be built in large quantities, which can be easily maintained on the cramped deck of an aircraft carrier in the middle of the ocean, and which will return the pilot home alive every time. The Corsair II was exactly such an aircraft, and that is why it outlived all its supersonic contemporaries, most of whom have long turned into forgotten lines in reference books, while it continued to fly, fight, and win.